In this video we'll look at the chemistry of how sarin works, and the first thing we'll do is just write its name on one line. There we are, sarin. There are two pictures here of the sarin molecule and also its chemical formula. The key part of sarin is this group of atoms here. It's an organophosphorus compound. In this drawing, the phosphorus, the oxygen and the fluorine are here, and in this slightly different drawing of the same molecule we've got the phosphorus, the fluorine and the oxygen here. If you are ever unlucky enough to come into contact with sarin, these are some of the symptoms that you might experience. And as you read down this list of unpleasant symptoms, you find that at the end it says respiratory failure. In other words, it does of course lead to death. And it's a remarkably small amount that you need in order to kill someone. About 0.5 milligram, especially if it happens to get into your system through your eyes or through your mouth and nose. You need rather more of it if it's only absorbed through the skin. Sarin has of course been used. It was used in Iraq by Saddam Hussein back in 1988. This was to put down a revolt by the Kurdish people, and thousands of people were slaughtered, not just using sarin but also other toxic gases such as mustard gas. Sarin was also used in Tokyo in 1995. A religious cult released sarin into the Tokyo subway and caused about 12 deaths and lots of illness. And more recently, as I'm sure you're aware, sarin has been used in the civil war in Syria, and the stockpiles of sarin are currently being destroyed. Now, sarin, of course, is known as a nerve gas. So what has sarin got to do with nerves, and how do nerves work? Well, this diagram shows the end of one nerve cell, let's call it A, and it wants to send a message to the next nerve cell, B, and you'll notice there's a gap between them. They don't actually touch, and the communication isn't electrical, it's chemical. What happens is a molecule called acetylcholine, which is symbolized by this little symbol here, is released from what's known as the synaptic vesicle. It diffuses across the cleft to where there is a receptor, and it binds to it, and that causes the signal from nerve cell A to nerve cell B. Now, as soon as that's happened, it's vitally important that the acetylcholine molecule is then destroyed, so that the system is primed, ready for the next time that nerve cell A wants to talk to nerve cell B. And the way the acetylcholine is destroyed is that an enzyme with this long name, acetylcholinesterase, chops the acetylcholine molecule into two bits. There's the choline and the acetate parts of the molecule. The choline, as you can see, is then absorbed back into nerve cell A, and it's resynthesized back into acetylcholine, ready for the next time that A wants to talk to B. And this whole system is perfectly well regulated. It's a beautiful sort of cyclic system. And what happens if sarin is present is that the enzyme acetylcholinesterase is inactivated. So that enzyme no longer works, and the whole cyclic system is broken down. So that acetylcholine here is not being destroyed as it should be after it's done its job. It's building up and causing all sorts of problems. The nerve cell A to B it's sort of short-circuited. It's constantly sending a message. Everything's out of control, and the result is all those unpleasant symptoms up to and including death that we thought about before. Now this is a picture of the enzyme acetylcholinesterase, and yes, it is a big scary molecule, but like all enzymes it's a protein, and proteins are polymers of amino acids. That means there are several hundred amino acids joined together into one enormously long molecule, which is then wrapped up into a specific three-dimensional shape as pictured here. And somewhere on the surface of this roughly globular molecule there is what's known as the active site. And this is a pocket or groove or cleft into which the enzyme substrate will fit. And the substrate is the molecule upon which the enzyme acts. In this case it's acetylcholine. And the substrate and the active site are made for each other, and the analogy which is always used to describe this relationship is that of a lock and key. The idea being that the substrate fits perfectly into the enzyme's active site in much the same way as a particular lock requires a certain key to fit into it and to operate it, and won't accept some other key. This shows the structure of the enzyme substrate, the acetylcholine molecule. And it has an ester group which in theory could react with water and be broken to produce acetate, and the rest of the molecule, which is choline, where we have an OH group connected to these other parts of the molecule. And that reaction, the hydrolysis, splitting this ester bond into the two products, if left to its own devices, that would be extraordinarily slow. It might take months and months for that to happen. And in the living cell, this reaction has to happen in a tiny fraction of a second. And that's where the enzyme comes in. The enzyme is a superbly efficient catalyst that speeds up the reaction by many orders of magnitude. So let's see now how the enzyme achieves the splitting of the acetylcholine molecule. And that huge three-dimensional molecule that we saw before, which the enzyme actually is, I've abbreviated to just ENS for enzyme. Inside the enzyme's active site there is one particular amino acid called serine, and serine has an alcohol group, an OH group, as the key part of its side chain. And what happens once acetylcholine is in the enzyme's active site is that that OH group attacks the carbonyl group of acetylcholine, and the choline molecule breaks away. So now we've produced choline, the enzyme's done part of its function, but at this stage the enzyme's serine amino acid in its active site has picked up the acetyl group. Here it is bound to the enzyme. But that's only temporary. What the enzyme then does very quickly is catalyze the attack of a water molecule on this acetyl group, and that enables the acetate ion, which is the other product of the enzyme catalyzed reaction, to be released. And now you see we've gone back to our original enzyme in the state it was to start with, and it's now ready to go back and just repeat the process over and over again. And it does that at least 10,000 times per second. It's a very, very efficient way of getting rid of acetylcholine. Now, I mentioned the lock and key theory before, and when you look at the chemical structure of sarin and compare that to the structure of the enzyme's natural substrate, acetylcholine, they don't look very similar. But nevertheless, it appears that sarin has got enough similarity in terms of overall shape and size to fit quite tightly and neatly in the enzyme's active site. So although it's not the genuine key, it's close enough that it does go into the keyhole. And when it's in there, the same key amino acid in the enzyme's active site, the serine molecule with its OH group, attacks the sarin molecule as though it were its substrate. And fluorine is displaced and ends up as hydrogen fluoride. And the whole of the rest of the sarin molecule is now connected to the enzyme's active site. But this time it's not a temporary process, it's a permanent process. The enzyme cannot rid itself of that group, and so we have effectively completely inactivated the enzyme. It can't go back to its original state, so now the enzyme's not working, acetylcholine is not being hydrolyzed, and nerve communication is going haywire because the acetylcholine is not being destroyed. And that is the way that sarin results in the horrible effects that it has.